This video covers section 7.2, Rational Exponents, for Math 95 at Linn-Benton Community College. Our goals in this section are to understand the meaning of a to the 1 over n, a to the m over n, a to the minus m over n, to simplify expressions with rational exponents, and to use rational exponents to simplify radicals. Essentially, all this section is a different notation for radicals, which we covered in section 7.1. In some situations, the square root notation will be more convenient, while in other situations, the radical exponent will be more convenient. The definition is here. A to the 1 over n, so the exponent is that fraction, 1 over n, is the same as the nth root of a. Now, remember back when we said that the definition of a square root was that it undoes x squared, so that the square root of x squared is the same as x, and the square root of x squared is also the same as x. In order for this rational exponent notation to make sense, we should verify that if we write the square root of x as x to the 1/2, that all of this still works. So let's check. Let's see if the square root of x squared still works out correctly using this rational exponent. So the square root will become a power of 1/2. So if I've got an x squared on the inside, it'll become x squared to the 1/2 power. Now remember that when I have a power to a power, I multiply exponents. So this becomes x to the 2 times 1/2. 2 times 1/2, and sure enough, 2 times 1/2 is just x to the first power, which is just x. So it certainly does seem to work that way. And while we're at it, let's check the other one. Let's check that the square root of x squared is going to equal just x. Remember that the square root now can be written as x to the 1/2, and then I'm taking that whole thing to the second power. But we're going to end up with the same situation here, since I'll have 1/2 times 2. So I'll have x to the 1/2 times 2, which is just x to the 1, which is x. So what this shows us is that this new notation for radicals does behave the same way that the radicals did. We knew that the square root of x squared should equal just x, and when I use this fractional exponent notation instead, I still get to the same answer. And similarly, we knew that the square root of x squared ought to equal just x, and this radical notation brings us to the same place. So they really are equivalent. They really do work out the way that we think they should. So that, of course, brings up the question, why do we have two notations if they both do exactly the same thing? At this point, it's kind of a matter of style. For a lot of students, the radical notation is much more intuitive, especially if the radicand is a nice number, something like the square root of 4. But if you do a lot of algebra, that rational exponent will become really convenient because you can use all the properties of exponents. And if you're going on to take calculus, that radical exponent notation will again become really, really convenient because you can use the properties of exponents. So at this point in your algebra career, wherever you're going, our goal is just to expose you to this new notation, get you a little bit comfortable with it so that it doesn't surprise you the next time you see it, and maybe even convince you that it could be kind of handy sometimes. So with that in mind, let's do a couple examples of going back and forth between radical notation and rational exponent notation. Here I've got the cubed root of 27. As a rational exponent, that is 27 to the 1/3 power. Whatever type of root it was becomes the denominator of the exponent. Now, whichever way you write this, the cubed root of 27 or 27 to the 1/3, this is still a little math problem that is asking what number multiplied by itself 3 times equals 27. And the answer to that is 3. So simplified, this is 3. Now go ahead, look at these next problems, try them out, see if you can fill in the rest of this table, and I will be back in just a moment. Go ahead and pause the video. Okay, did you take a moment to try each of those problems yourself? Then let's look at them together. So here I had 16 to the 1/2. In radical notation, that is the square root of 16. Remember, the denominator of the rational exponent becomes the type of radical that it is. Now, if I just look at the square root of 16, I remember that that's 4, since 4 times itself is 16. This next one is a little bit more tricky, isn't it? I started with the 4th root of 16x. Now, to translate that over into a rational exponent, I just take all the stuff under the radical and take it to the power of 1/4. Again, remember that whatever type of radical it was is what became the denominator of the exponent. To simplify that, I'm going to go ahead and look at it back over here as the 4th root of 16x. Now, 16, the 4th root of 16 is 2, since 2 times itself 4 times is 16. However, there isn't anything nice to do with the x, so it can either stay as x to the 1/4, or we could write it as 2 times the 4th root of x. Either one of those would be acceptable. On this one, we were looking at negative 27y to the 6th, all to the 1/3 power. So first we rewrote that with radical notation, taking all that stuff in the parentheses, negative 27y to the 6th, and putting it under the radical and using a cubed root. Now we'll go ahead and simplify it. What times itself 3 times is negative 27, negative 3, and what times itself 3 times is y to the 6th, and that would be y squared. Now notice over here, if I thought I have a power to a power, y to the 6th to the 1/3 power, I could multiply those two powers. 6 multiplied by 1/3 is 2. That's not a coincidence. That'll work out every time. Finally, in this last example, we had 7x to the 1/5. Now notice that the 7 is not being taken to the 1/5 power because it's not in parentheses with the 1/5. So this gets rewritten as 7 multiplied by the 5th root of x. That doesn't really simplify at all. So we could either write it 7 times the 5th root of x or 7 times x to the 1/5. Again, either one of those would be an acceptable answer. After those last couple examples, hopefully you're starting to get the feel for this new notation. If you don't feel totally comfortable with it yet, don't worry. It takes a little practice to get used to this. It's like learning a new language. We are going to keep adding on to that knowledge though. Consider this. I have the cubed root of x to the 5th power. I'm going to go ahead and rewrite that in my new notation. Remember that the cubed root of x is x to the 1/3. And now I've got all of this to the 5th power. Now we noticed earlier that when I have a power to a power, I can multiply those powers. So this becomes x to the 1/3 times 5. But 1/3 multiplied by 5 is x to the 5/3. So maybe I could have skipped straight to this step and written the cubed root of x all to the 5th as x to the 5/3. Sure enough, that leads to our new definition. A to the m over n is the nth root of a to the m, which is the same as the nth root of a to the m power. Now let's dig into that for just a moment. This first equality is telling us that if you have something to a rational power, the denominator tells you what kind of root it is, what kind of radical, and the numerator tells you the power on the thing inside the radical. This second equality is telling you that it doesn't really matter what order you do those two things in. You can either take the number to the power and then take the radical, or you can take the radical and then take whatever you get to the power. Either way, you'll get the same answer. Finally, as long as we're writing down new rules, let's write down this one. If I have something to a negative power that happens to be a fraction, that's the same as 1 over the thing to the power. The fact that the power is a fraction doesn't really matter. This is just that same old rule that you knew about negative exponents. If you have something to a negative power, that's the same as 1 over the thing to a positive power. If the power happens to be a fraction, no big deal. Okay, let's practice. It really does take a lot of practice to get the hang of this. I'm going to go ahead and simplify each of these three expressions while you watch, and then I've got a whole page for you to try on your own before I show you the solutions. This first one is 9 to the 3/2. So that is the square root of 9 cubed. You can write it either this way, the square root of 9 cubed, or we can write it as the square root of 9 cubed. Remember that we had two options there. We could do it this way as well. I'm going to go ahead and work it out both ways this time, just so that you can see that we really do get the same number in the end. I'll go ahead and work out the one in red first. So first I'll find that 9 cubed is 729. So that leads me to have the square root of 729. And then I use my calculator to take the square root of 729 and find that that is the number 27. Over here in the green, I've just written it down the other way. I've written down the square root of 9 first and then cubed it. So the square root of 9 is 3, and 3 cubed is 27. So it works out the same either way we do it. This way happened to be a little bit easier for me because I was able to do each step in my head without having to ask the calculator. This second problem says negative 256 to the 3/4. Now notice that it's not parentheses, negative 256 parentheses to the 3/4, which means that that negative is not under the radical. So I'll go ahead and rewrite this with a radical as negative the 4th root of 256 cubed. I'm going to write it this way with the cubed all the way on the outside because I think it'll be a little bit easier to find the 4th root of 256 than to cube 256 and then find the 4th root. Whatever I end up with though, my answer will be negative. So first I'll go ahead and ask my calculator what the 4th root of 256 is, since that's not one that I know off the top of my head. However, it turns out to be 4, since 4 multiplied by itself is 256. So now I have the opposite of 4 cubed. 4 cubed is not too bad. That's just 64. So my answer is negative 64. I should point out that you can actually punch this in on your calculator just like it says here. I can just punch in negative 256 to the power of 3/4. Notice I'm putting the power 3/4 in parentheses so that the computer knows that the whole 3/4 is in the exponent. When I hit enter, ta-da, I get negative 64, the same answer that I got when I did it step by step. Okay, my final example is negative 16 to the negative 3/4. Now again, notice that the negative is not in parentheses with the 16, which means that the negative part is not being taken to the power of negative 3/4. Basically, that tells me whatever my answer is, I'll end up making it opposite at the end. That power of negative 3/4 tells me that I'm going to flip this down to the bottom of the fraction. So I'm going to make this negative 1/16 to the positive 3/4. Again, notice that the negative in front of the 16 didn't change when I moved it. Only the power on the exponent changed. Now that I've rewritten everything with positive exponents, I'm ready to figure out what this could be. This is negative 1/4 the 4th root of 16 to the 3rd power. Now the 4th root of 16 is something that I know. That's 2, since 2 times 2 times 2 times 2 is 16. So this will become negative 1/2 cubed. And again, 2 cubed is something that I know, which is 8. So this is negative 1/8. Now, as promised, I have several expressions for you to simplify. Go ahead and pause the video, and when you come back, I'll have worked these out and we'll talk through them. And we're back. I'm going to go ahead and talk through each of these problems that we've solved. Starting with 16 to the 3/4. So 16 to the 3/4 is the same as the 4th root of 16 cubed. Notice again that the denominator of the fraction became the type of radical, and the numerator became the power that we're taking everything to. Now I can use the order of operations to simplify. The 4th root of 16 is 2, and 2 to the 3rd power is 8. My second problem is negative 32 to the 1/5 power. So that is the 5th root of negative 32. Notice that I didn't bother to write that this is all to the 1st power, since anything to the 1st power is just itself. Now the 5th root of negative 32 is asking what number multiplied by itself 5 times is negative 32. That turns out to be negative 2. If you don't know that off the top of your head, that's okay. You can go ahead and ask your calculator what the 5th root of negative 32 is. Next up is negative 16 to the 3/4. Now this looks an awful lot like 16 to the 3/4, except that there's a negative out front. So really, all that means is that I'm going to get the same answer as 16 to the 3/4 and then make it negative. So it's no surprise that the answer that I end up with is negative 8. We'll go ahead and walk through the steps anyways. That negative stays out front since it's not in parentheses with the 16. And the 16 to the 3/4 can be written as the 4th root of 16, whole thing, cubed. The 4th root of 16 is 2, 2 cubed is 8, and that negative that was still out front now applies to the 8. Last up, we have 27 to the negative 2/3. The first thing that I'm going to do is rewrite that to be a positive exponent, 1 over 27 to the positive 2/3. Now that the negative on the exponent is taken care of, I can move on with my life. And 27 to the 2/3 is the same as the cubed root of 27 squared. The denominator of the exponent becomes the type of radical, and the numerator of the exponent becomes the power. The cubed root of 27 is 3, so now I have 1 over 3 squared, and 3 squared is just 9, which gives me a final answer of 1/9. I should point out that on each of these problems, I chose to rewrite the rational exponent in such a way that we did the radical first and then took the whole thing to the power. I want to remind you that it's completely acceptable and the same to rewrite this instead with the radical on the outside and the power on the inside. So 16 to the 3/4 is the same as the 4th root of 16 cubed. The reason that I chose not to rewrite it in this way is because 16 cubed is a huge number. So I end up with the 4th root of 4,096, which frankly I don't know off the top of my head. However, I can always ask the calculator, and the calculator will tell me that the 4th root of 4,096 is 8. We get the same answer either way. When you're computing something by hand, it's often easier to rewrite it this way, where you have the radical first and then do the power. However, it is completely acceptable and will get you to the same answer if you rewrite it this way, where you do the power first under the radical and then do the radical. Now that you've been exposed to some of that new notation, it's time to remind you that all of the exponent rules that you've learned in the past can be used with rational exponents. Remember, those fractions are just numbers. You can use all the same exponent rules that you know with those numbers. So let's take a moment to remember what those exponent rules are. I'm just going to write down an example for each of these rules. The product rule said that if you have something like x to the 5th times x squared, you can add those two exponents, making this x to the 7th. The quotient rule said that if you have a quotient, something like x to the 5th over x squared, you can subtract those exponents, which gives you x to the 3rd in this case. The power rule said that if you have a power to a power, you multiply the powers. So if you have x to the 5th, and then that whole thing is being squared, you can multiply those two exponents to get x to the 10th. The power rules for products and quotients just meant that if you have two things that are both being raised to a particular power, such as x times y to the 5th, you can rewrite that as x to the fifth times y to the fifth. And similarly, if you have two things being divided and they're being taken to a power, you can rewrite that as x to the fifth over y to the fifth. The zero exponent rule was just the rule that anything to the zero power, whatever it happens to be, is just 1. So whatever I have, if it's being taken to the zero power, my answer will be 1. And finally, the negative exponent rule, you've actually already been reminded of. If you have something like x to the negative 2, that's the same as 1 over x squared. Or if you have something like 1 over x to the negative 2, you can flip that up to the top of the fraction to make that regular x squared. Now that I've reminded you of those rules, you can imagine what's coming next. I'm going to want you to simplify a whole bunch of expressions by using those rules. I'm going to start by showing you these two, and then I have a few on the next page for you to practice. Here I have 9 to the 2 fifths over 9 to the 12 fifths. Now, these two things have the same base, which means that I can rewrite this as 9 to the 2 fifths minus 12 fifths. Yeesh. Now, you might want to make this a little problem all on its own. 2 fifths minus 12 fifths, do it off to the side, and see what you get. However, these two fractions already have the same denominator, which makes this a lot better. That means I only need to subtract the numerators. 2 minus 12 is negative 10, so I'm going to end up with 9 to the negative 10 fifths. Wait a second. Negative 10 fifths is the same as negative 2, so this is just 9 to the negative 2. Well, hey, I can do something about that negative exponent. I can make it 1 over 9 squared. And finally, 9 squared is a number that I can compute, so this is 1 over 81. The second problem that I have here is x to the 1/4 all to the 6th power. Now remember, that is the same as x to the 1/4 multiplied by 6. Again, I think it's sometimes helpful to take this little problem, pull it off to the side, and do it separately. 1/4 multiplied by 6. Remember that I can think of that as being 6 over 1 to make that multiplication a little easier, and then I multiply straight across. You can cancel before or after doing that multiplication. Notice that 2 will go into 4 twice and into 6 3 times. Now when I multiply straight across, I'm going to get 3 halves. That means that back over here, I had x to the 1/4 times 6, but I just figured out that 1/4 times 6 is really just 3 halves. So this becomes x to the 3 halves. Now, x is not a particular number the way that 9 was, so I really can't do anything after this. You can leave your answer as x to the 3 halves. Typically, it is also acceptable to leave this as the square root of x cubed or the square root of x cubed, since we've seen that these are all the different ways of saying the same thing. Any of these would be acceptable on a test. Okay, so I keep telling you that practice is what you need to get the hang of this stuff. So go ahead and take a moment and try practicing each of these 3 problems. Try to simplify it as much as possible. Pause the video, and when you've given each of them a shot, check back in and we'll talk through each problem together. All right, did you give each of those problems a try? Let's go ahead and look at them together. X to the 1/3 times x to the 1/4. I have two things with the same base being multiplied, which means that I can add their exponents. I end up with x to the 1/3 plus 1/4, whatever 1/3 plus 1/4 turns out to be. I decided to do that problem down here using a little bit of scratch work. I ended up with 7/12. So this is x to the 7/12. I would like to remind you that you can use your calculator to do some of this fraction stuff if you're feeling uncomfortable with it. Let me show you how to do 1/3 plus 1/4 in your calculator and get a fraction as an answer. Okay, here I've got my nice TI-83 calculator. Your TI-84 will look about the same. and I want to do 1/3 plus 1/4 and get a fraction as an answer. So I start by entering 1/3 plus 1/4. It's always a good idea to put your fractions in parentheses. It lets your calculator know that you want it to compute the 1 divided by 3 part before it does anything else. So I entered 1/3 plus 1/4, and I hit enter. And I get 0.58333333 and so on, a nice repeating decimal. Now that's not something that I instantly recognize as 7/12, but you can use this math key to get to something that will allow you to turn it into a fraction. Math takes you to a menu. The very first option is to fraction. Hit enter. Now it's going to take your previous answer and turn it into a fraction as soon as you hit enter. And sure enough, it tells me that my answer is really 7/12. So again, if you're feeling uncomfortable doing some of this fraction addition, feel free to use your calculator. All right, back to our examples. Here I had y to the -3/4 times y to the 10/4. Again, I have two things of the same base being multiplied, which means that I can add their exponents. -3/4 plus 10/4. This time my life is a little bit easier since I already have a common denominator. -3/4 plus 10/4 is 7/4. So my answer just is left as y to the 7/4. My last problem looked the worst. I'm going to start by looking first at the numerator. I have 3x to the -2/3 all raised to the 3rd power. I'm going to take care of that all raised to the 3rd power first. Remember that when I have two things together being raised to a power, I can do that power to each one individually. That gives me the 3 cubed and x to the -2/3 times 3, since a power to a power means that you'll multiply the powers. So I just wrote down everything that I have so far. 3 cubed, x to the -2/3 times 3, all over x squared. Off to the side, I went ahead and did that multiplication. -2/3 times 3 is actually just -2. So in my second step, I realized that 3 cubed is just the number 27. X to the -2/3 times 3 is x to the -2, and that x squared on the bottom hasn't changed at all. Now I'd like to deal with that negative exponent on the x to the -2. I can move it downstairs in the fraction to turn that into a positive exponent. Now I have 27 over x squared that was there originally, and the x squared that used to be on top, but is downstairs now. X squared times x squared is x to the 4th. So my final answer is 27 over x to the 4th. Our last goal in this section is to use this rational exponent notation to make dealing with radicals maybe a little bit easier. What we're going to do is start with radical expressions, rewrite them with rational exponents, simplify the fractions, and then go back to radical expressions. We're going to assume that all the variables are positive numbers so that we can avoid using that absolute value notation. You'll notice that in the directions to problems in your textbook, it's going to say the same thing. Something like, assume that x and y are positive numbers. That's really just trying to make the problem easier for you. It's not meant to be more confusing. Okay, let's do a couple examples. Starting with the 10th root of b to the 5th. Now, first I'm just going to rewrite this using rational exponents. I'll have b as my base. Because the 10 is the type of radical, that will be the denominator of the exponent. And since b is being raised to the 5th power, that will be the numerator. Now I have b to the 5/10. Now if I just had the fraction 5/10, you'd look at that and pretty quickly tell me that that's actually 1/2. So this is the same as b to the 1/2 power. Well, remember that b to the 1/2 power is the same as the square root of b. Ta-da! So hopefully the square root of something looks a little bit better than the 10th root of that thing being raised to the 5th power. Next up is the 9th root of x cubed y to the 6th. So again, remember that the 9 here is going to become the denominator, and the power on the inside is going to become the numerator. So this will become x to the 3/9, y to the 6/9. Each of these are fractions that can be simplified. X to the 3/9 is x to the 1/3, and y to the 6/9 is y to the 2/3. Then we're going to go ahead and turn these back into radical expressions for practice. X to the 1/3 is the same as the cubed root of x, and y to the 2/3 is the same as the cubed root of y squared. Last thing with this problem, because we have the same kind of root and it's being multiplied, we can smash these together into one radical and make this the cubed root of x times y squared. And that's definitely as simple as that will get. Finally, I've got the 4th root of 9. That doesn't immediately look like a problem like any of these. But remember that 9 is 3 squared. That's right, this one's trying to be a little tricky. Now I can rewrite this as 3 to the 2/4. Well, 2 over 4 is the same as 1/2, so this is 3 to the 1/2. Aha, that 1/2 power is just a square root, so this is the square root of 3. Turns out the 4th root of 9 is the same number as the square root of 3. Go ahead, you can check it on your calculator. Okay, last thing is some practice for you. Same directions. You're going to start with radicals, rewrite them as rational exponents, do any simplifying that you can, and then put them back together as radicals. Go ahead and pause the video, give these each a try, and then start up again and we'll talk about them together. And we're back. I started with the square root of y times the cubed root of y, and then I rewrote those as y to the 1/2 times y to the 1/3. Then I noticed that if I have the same base and they're being multiplied, I can add the exponents. So I figured out that 1/2 plus 1/3 is 5/6. So this becomes y to the 5/6. Rewritten as a radical, that's the 6th root of y to the 5th. We actually just did this middle one in the last slide, so hopefully without too much trouble, you were able to get this to be the cubed root of xy squared. Last example, we had the cubed root of x over the 4th root of x. I rewrote each of those radicals as rational exponents, making it x to the 1/3 over x to the 1/4. Then I noticed when I have the same base being divided, I can subtract the exponents. Then I figured out that 1/3 minus 1/4 is 1/12. So that gave me x to the 1/12. Rewritten as a radical, that's the 12th root of x. Before we go, I want to say that I know that this stuff with rational exponents and all the exponent rules can seem pretty abstract. Remember that our goal here is just to expose you to this new notation and remind you of all those exponent rules. We give you a lot of complicated problems because we want you to be comfortable using this notation and using those exponent rules so that it's not a stumbling block for you later on in your algebra career. So with that in mind, go ahead and get some practice done by working on your homework.